Hello, Professor Hildebrandt here. So this is my final content lecture for the last part of Chapter 5. The um, rules that we were doing in probability in the first two portions of the chapter, and then I'm going to introduce a new additional measurement that we use. Is called counting, and so we'll have a few ways that we can do some counting. But first we're going to talk about contingency tables. And so this is a way to classify our observations with more than two categories. And so in this example here, we had a sample of 150 adults, and they were asked both their gender and the number of Facebook accounts they used, 0, 1, or some had 2 or more. So you can see our total sample size here was 150. That was broken down into 70 men and 80 women. And that 150 is also broken down into 60 of them have no account, 70 have one account, and then 20 have 2 or more accounts. The textbook walks through the example on movie tickets and based on age. But so I'm going to talk some more about calculating some probabilities from this table with the Facebook data. So here we go. So first, what if we wanted to find the probability that a randomly selected person from our sample does not have a Facebook account? And so we're going to be looking at this first row of information. This is the values of the people that don't have a Facebook account. We have 20 men and 40 women. And so in total for our sample, 60 individuals do not have a Facebook account. We're looking for anyone that doesn't. It's not gender specific here. So we're going to use the total number for our sample of 150. And so this is just a kind of basic probability here. The probability that the person does not have an account, has 0 accounts, is the 60 possible out of the 150 for the sample. And so our probability here would be 0.4. So that one's pretty straightforward. Okay, well, what about the second scenario? Find the probability that a random person has at least one account. So this one's different because we're going to have 2 rows of information that we have to consider. The second row here, totaling 70 people, those people have one account, but we also have to include row 3 with 2 or more because, again, look back to it says find the probability has at least one. So anything more than one we want to include. So we're going to have to combine 2 outcomes here. The first outcome, there's 70 people possible. The second outcome, 2 or more accounts, there's 20 people possible. Again, those numbers come from this last column here. These 2 outcomes are what we would call mutually exclusive. This means that a person cannot be part of the 70 and also part of the 20. If you have 2 or more, you're not counted in the only having one. Because of this, we're going to use the special rule of addition that I went over in one of the earlier lectures. Again, we're looking for anyone that has at least one. So we're going to be using this total sample size of 150. So we're looking for the probability that you have 1 or 2 or more accounts. Well, the probability that they would randomly select someone that has one account is 70 over 150. And we're going to add to that the probability of selecting someone with 2 or more, 20 over 150. So you get 0.375 plus 0.125, or our probability here is 0.5. So I'm trying to build up the level that we're working on. So let's take it one step further. Find the probability that a randomly selected person has 2 or more accounts and is a man. Now, this is what we would call a joint probability because the second outcome, being a man, is conditional on the first occurring. So first, what's going to occur? They have 2 or more, and then what's the probability that the person that has 2 or more that was selected is also a man for the gender. So here we're going to use the special rule of multiplication. So first we need the probability that the person selected has 2 or more accounts. Again, that's kind of the straightforward piece. So there's 20 possible that are in this row out of the 150 sample. So the probability there is 0.133. But then we need that conditional probability, the probability that the person selected is a man who has those 2 or more accounts. And so if we look within the 2 or more, there's 10 men that fall into that classification out of a possible 20. It's important to note here, we're not dividing by the 150, okay? We are only dividing by what is possible to be in that grouping, which is only 20 individuals. And so the probability there would be 0.5. We multiply those two together, and the probability that a randomly selected person has 2 or more accounts and is a man, it's really low. It's 0.067. So hopefully this shows you guys how we can use contingency tables, and we can pull data from those to calculate different probabilities. Another thing that we can do is we can take a contingency table and create what's called a tree diagram. And so this is a visual way to help organize and calculate probabilities to then help us make some decisions. And so this was the example I was referring to earlier that your textbook talks about in great detail. It's looking at the number of movies a person watches per month based on their age range. And so, a theater could use this to maybe try to decide, should we offer a senior discount maybe for those that are 60 and older. And so if you look then with me at the next slide, so you'll see then this is the tree diagram. And so we start here with the age, and the probability that they are 30 or younger is right here, the 100 divided by 500 or 0.2. The probability that they're 30 to 60 is here at 0.45, and then 60 or older, 0.35. But then we can break it down more. So by age, we can break down how many times a month are they going to the movies. And so, again, the tree diagram is just kind of a visual way to take the information from a contingency table and maybe help us make some decisions based on comparing probabilities for different groups. So the final part of this chapter goes over the principles of counting. Don't get confused here. It says multiplication formula. This is different from the 2 multiplication rules that we discussed in section 2 of this chapter. So we're going to cover 3 different counting formulas that are useful to help us determine the possible number of outcomes in our experiment. And so this first one here, the multiplication formula, and we give you the formula here, the total number of arrangements is m times n. It is helpful when we're trying to find the total number of possible arrangements for 2 or more groups. So it can be used for more than 2 events. We could have m times n times o times d. Okay, we could keep going. But so for this example, and this one's pretty easy to see, you can buy a car. It can be a convertible. It can have 2 doors. It can have 4 doors. But then you can also have different wheels. You can have wire wheel covers or solid wheel covers. And so how many different vehicles are out there? Well, there's 3 different models here. There's 2 different wheel options. And so it's a combination of, there's 6 different possible vehicles that you could purchase. And so that's how we would use this basic counting one. The second one is called the permutation formula. So these next 2 cover a mathematical concept that you guys may not remember called a factorial. Some calculators do have an option on this, and Excel can help you calculate these as well. But I'm also going to show you how to just do it out by hand. But this one is used to find the number of possible arrangements when there's a single group of objects. And so like this example they give, there's 3 electronic parts to be assembled. They all have to be inserted into this plug-in component that you're making. And so your formula here is n factorial, so whatever your n is, the total number of objects, divided by n minus r, r being the number of objects that have to be used, and that the difference between those two also being a factorial. And so mathematically, we plug those numbers in, 3 and 3, 3n, 3r. We would get 3 factorial divided by 0 factorial, and you just have to know that 0 factorial by definition is equal to 1. And to do the factorial, it's the number times all the other numbers less than that until you get to 1. And I'll show you in a second. So this 3 factorial, we would write it out as 3 times 2 times 1, which then divided by 1 equals 6. And if you see, if we label our 3 parts A, B, and C, there are 6 unique combinations, 6 different ways we can organize those 3 parts. When we're using the permutation formula, the order of the objects matters. So putting the parts together in the order of A, B, and C produces a different yield, a different final product than putting the products together in the order of B, A, C, and so on and so forth. And this is important because the third formula I'm going to show you, the order of the objects doesn't matter. So let's do that one. So this one's called the combination formula, similar to the permutation, but again, now the order doesn't matter. So we were talking about 3 parts, right? What if I need to create a committee of 3? Well, having a committee of 3 that's comprised of Amy, Joe, and Karen, that says the same thing as having a committee that's Karen, Amy, and Joe. It's the same 3 people. It doesn't matter what order I put their names in. And so we need a slightly different formula to then help us calculate the number of possible outcomes from this arrangement when the order is not important. So N still stands for the total number of objects, and R still stands for the number of objects to be selected. But now our formula is N factorial divided by R factorial times the difference between N minus R factorial. So here we've got this theater, and they're using teams of 3 employees to work their concession stand. They've got 7 employees available to work. How many different teams can be scheduled? So total number of objects are those 7 employees. So that goes in our numerator, 7 factorial. And then for our denominator, our R, the number that we're selecting, we're making a team of 3. So our R is 3, and again, our N is 7. And so you end up with 7 factorial divided by 3 factorial times 4 factorial, and the answer is 35. Let me show you how we get there, because I know, like myself, you guys probably get frustrated when math skips some steps. So again, remember that the exclamation point means factorial, and that you multiply that number by every number lower than it until you get to 1. Also keep in mind, by definition, 0 factorial is 1. So again, how did the book get from this to an answer of 35? Well, I think we can hopefully understand how we got here. You understand the difference between 7 and 3 is 4, and then they just took away the parentheses because this also means 3 factorial times 4 factorial. So let's start with our numerator, 7 factorial. This is what I mean by multiply by every number until you get to 1. So 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by our denominator. 3 factorial then is 3 times 2 times 1, and 4 is 4 times 3 times 2 times 1. Whew, okay, so the nice thing about these factorials, you guys, though, is we're dividing here. And so cancel out, obviously the 1s don't matter anyway, but these 2s would cancel each other out. These 3s would cancel each other out. The 4s, again, the 1 we can ignore. And so if you multiply 7 times 6 times 5, you would get 210. And then 3 times 2 is 6, and 210 divided by 6. Now we have it. This is how the book gets that final answer of there are 35 possible different teams to work the concession stands. I hope this helps wrap up this chapter. But as I've done for the first 2 sections, I will post at least 1 more, perhaps 2 more examples of working out some of these probabilities.